So let's get started. So you know that the schedule. So we are here module 15, and then we'll talk about the physical database design, part 2. Mm, You know that the assignment 6 and discussion 6 due date is the Friday. Okay, so please submit and complete and submit by the due date. And then, and this class is the last class of this semester. So the following week, Thanksgiving holiday, but we have a lot of work. I hope you enjoy. And then final project due date November 30th. And the final reflective assignment November 30th. And the student course evaluation December 3rd. So please submit your work by the due date. Make sense? Okay. Yeah. Yeah. Reflex assignment will be, you can find module 16. There is no template. Just open the Microsoft Word or any kind of text editor, and then just to write maybe what is the most interesting topic or least topic, and then your feedback, comments. That's all. Maybe there's no requirement about how many pages, maybe half page or less than half, doesn't matter. But the student course evaluation is officially the MGA will send the email, the link. So you can go to the link, and you can maybe select, I'm not sure. So it's the different things, okay? Then let's, maybe nobody comes here. So last week, I just mentioned about the hashing file to generate index table. So there are three types of approach to create index table. One is the simple linear file, and the second one is to use the B plus tree, and third one is hashed file. So let me show how to create the hashing, the table, hashing index, okay? So here, you know that what is the hashing? Maybe like usually you can use a modular reminder operator if you have a 10 array, something like that, maybe 0 to 9. If you have some the key value, maybe 20. So 20 modular 10 means it will be 0. So there 20 will be inserted to the index 0. Maybe 21 modular 10 is 1. So in this case, 21 is inserted index 1. So like this. This is a hashing, okay? So, but the problem is that if you have the complete, for example, 30 should be inserted. In this case, 10. Demand is 0. So if you go to the index 0, is already occupied by 20. So this is called the complete. So we have to avoid those kind of conflict. In other words, we have to find the appropriate cell array to store the 30. So one is that one approach is the linear probing. That is, for example, this is how many array from 0 to 10 is a total 11, right? So use modular remind operator, and then when you try to add 44 reminder 11 is what? It's a 0. So 44 is inserted index 0. About 4 modulo 11 is 4. 16 modular 11 is 5. 28 modulo 11 is 22 6. Okay, so here. But the problem is that when you try to insert 26 case, 26 oops, 11 with 4. So go to the index 4, but is already occupied by 4. So by the linear probing means just increment the index. 4 is occupied. Okay, go to the next. 5. But 5 is already occupied. Okay, increment 6. But 6 is already occupied, 28. Okay, increment 7. It is available, it's empty. So 26 is inserted at index 7. That one is a linear probing approach. Okay, but the power of the linear probing approach is, as you can see, in this area, it is called the clustering problem. So specific area, the cells are occupied. The others here and here is available. So the linear probing the approach has a clustering problem. So we have to avoid this. That means I'd like to scatter the occupied cells randomly, something like that. So we use the quadratic probing. So quadratic probing is similar. Maybe 44, 4, 6, and 28. If you try to insert 26, it's already occupied by 4. In that case, we can use this formula, quadratic formula. The J is just the index. The try to insert square. For the first try, J equal 1 means 1 square. Okay, go to there, but occupied, and try is number of tries or increment is 2 square 4. Okay, so from the original position 1, 2, 3, 4. Index 8 is available, so 26 is inserted there. This is a quadratic probing to avoid clustering problem. Okay, and next one, another approach to avoid clustering problem is double hashing. Double hashing means we can use the double hashing function. But in this case, that one is called, in other words, hashing function. That is the first hashing function. Like that. In this approach, we use the secondary hashing function. So 45, there, 58, 4, and 28. But if you try to add 12, so total 11, so 12 modular 11, it will be 1. But it's already occupied by 45. And then in this case, you can use the double hashing function. This is a first hashing function, and this is a second hashing function. So the second hashing function can be defined by the developer. You can design something like that. But in this case, for example, 7 minus key modulo 7 is used as a second hashing function. So 12 modulo 7 is 5. 7 minus 5 is 2. So it will be 2, and this is 1. So 1 plus 2 is a 3. So go to the index 3, but it's already occupied 58. And apply one more time hashing function, but a little bit change it. So 2 times 2 plus 1, it will be 5. So go to the index 5. Oh, it's empty. So 12 is inserted there. So this is double hashing to avoid the clustering problem. Make sense? And next one is separated chaining. So simple. In this case, we don't use quadratic probing and double hashing. Just insert the complete key into the same index. For example, the 4 is store index 4, but 26 is inserted 26 inserted to the index 4, but we have another data structure, something like that, like a linked list. So this is index 4, the following indicating the element key value is 4. If conflict is occurred, the first element indicating the second key, 26. If there are another one, like this. If there are another one, like this. This is a separate chaining. But the problem is that in order to store those kind of multiple key into this hashing table, we need another data structure. But in this case, a linked list. Okay, linked list. Okay. We're able to implement array. It's up to you. Okay. So this is another approach to create hashing table. So using those kind of the approach, we are able to create the hash table. The hash table, why we are generate hash table or P plus 3 or simple linear table is to support direct access. If you have a table in a database, and then maybe there are some data ID and the name and email, something like that. And there are some records like this. Maybe Christina and Nicole and Isabel, Caleb, and so on and so on. So if the direct access is supported in your database, we don't have to search from the beginning. That means sequential searching, we don't need that. Just can pinpoint the record that I want. That is called the data access. So in order to support this data access, we need index table. So index table can be implemented by this simple linear table or P plus 3 or hash file, hash table. Make sense? Okay. This is the first part. the second part. Maybe someone, no. The second part, here the physical database design starts when the logical database design ends. So after finishing logical database design, such as split into the separate table, satisfying normalization, the normal form. After that, we have to, maybe you may perform the physical database design. Okay? So take a look at this. So what kind of the inputs and the factors we have to consider for physical database design? First of all, the table. This is core produced by logical database design. And then we have to consider business environment requirements, data characteristic, application characteristic, operational, hardware and software characteristics. You may consider all of them for the physical database design. So if you have a question, just let me know. We only, it's on you. That said, our physical database design is starting after finishing logical database design. So when you finish logical database design, you know that no data redundancy and no anomaly. Okay, there are the main goals of logical database design is to remove anomaly, update anomaly, insertion anomaly, and deletion anomaly. And then the other one is to remove the redundant data. Okay. And then in our normal forms in the logical database design, the tables are connected using what? Foreign key, right? Foreign key. So using the foreign key, we are able to combine. It's called a join, right? But important thing is sometimes from the point of view, performance point of view, it cannot be acceptable. So according to the survey or research, the users click the website. When you visit the website and then request some a comment, and then they leave that website, the result is not returned less than 5 seconds. That means when I click the button and then wait 5 seconds, but after 5 seconds, they leave the website and they try to find another website. So important thing is the result should be returned less than 5 seconds. But it depends on the survey or the research. But anyway, 5 seconds is not long. It's very short time. So this is a key factor to estimate the performance. Okay. But when you click the button, it takes maybe 1 minute. Nobody used the website, right? So the performance is not acceptable. So that's why we need to do physical database design. Okay. Then here, the factors, business environment requirements, there are main requirement, response time, and then throughput. The response time, 5 seconds, 7 seconds, 10. It's up to you. It depends on the system. So the definition of response time, enter key is pressed to execute query until the result appears on the screen. That is a response time. If the response time is longer, you just leave, nobody use your system. Okay. And throughput. Throughput is kind of a little bit tricky concept like that. If you have a system and there are a lot of the users send the request to the system, maybe per second or usually per second. This is a system. And then there are a lot of users, user 1 and user 1 million, something like that. And they send request. But the hardware and software, the capability of the system is limited. So it cannot accept and handle all the requests at a given time. Maybe 1 million requests are arrived to the system, but given time, maybe 1 second, it can process the half, maybe not half. Half means 5 times 10 to the power 5. It's a half of 1 million requests. In this case, you can say that it's a total the total number of requests, and then the processed request by this system. It will be 0.5. In other words, this throughput is 50%. But if the system is so powerful, so if the system process all the requests, something like that, it will be 1. That means throughput is 100%. Okay, that is the throughput, the concept. So that factor also should be considered for physical database system. Okay. And then data characteristics. How much data in a database? How many records? In a table, there are 300 rows, 30,000 records, and 3 million records, and 3 billion records. Depending on the size of the data, the performance will be different. For small, performance will be good, but maybe 3 million and 3 billion, the performance will be bad. It's worse. So we have to consider the volume, the data volume. And then, and the other one is how often data is updated. Every second, if the data is updated, insert it, and then delete it, and update it, something like that, it affects the performance. Okay, so that factor should be considered for physical database design. And then application characteristic, like what is the nature of the application? They will use the data, which application is the most important, which data will be accessed by each application. For example, like, so which database table does each application require? And do the application require that table joins? And how many applications and which specific application share the specific tables? And how often application use a particular table, frequently or infrequently? So that means if you have the database, and then you may like so financial department and process office and like a facility and student academic affairs, something like that. Okay. So depending on the department, they use different kind of application. Okay. So application 1, for example, and application 2, application 3, and application 4. So application 1, this is a DB of the MGA, for example. Try to get some specific the table in a database, maybe financial department, maybe table about uh, tuition or the fee, something like that, this table. And then process also used that table. Facility, try to access a building table and construction table and so on and so on. Academic affairs, use student, faculty, staff, and so on and so on. So depending on the application, the tables are accessed are different. So when you design database and application, we have to consider the characteristic of the which application, okay, for the design. Okay. Then priority. So when we update the table for better performance in a physical database design, but it prevents performance of another application. In this case, like if we have a table here, well, from the point of the application 1, maybe if we already changed this table for better performance, but from this financial department, the performance is good, but maybe academic affairs, from the point of academic affairs, the modification of this table can be worse. The thing we have to think, this application is more important or this application is more important. Which application is more critically important for service? Okay, so design is not just a simple step. We have to consider those kind of things. So this is the application priority. Okay, then security and then backup recovery. Okay, just take a look at this one. And DBMS characteristic, hardware characteristic, it's the same. Consider those kind of things. And also, so if you perform the physical database design, that modification of the table or DB can change logical database design or cannot change the logical database design. So we have two parts, the physical database design, category and technique, not change logical design. But the other one is change the logical design. It's a two part we have to consider. So, for example, adding external features, reorganization, data, splitting table into multiple tables, those kind of things. The physical database design doesn't change logical design. Okay, but here changing attributes, adding attributes, combining table, adding new table, those kind of things change the logical, the design. Okay. So first of all, adding index. What is the index? Index is I erased. Index table is to support direct access for better performance, right? So for index can be index table can be implemented by what? Simple linear table and p plus 3. The other one is hash table. Okay. By 3 approaches, we can create index table. So index table doesn't change the table itself. So think about that. Maybe okay, take a look at this example. This is a general hardware company. So salesperson table, customer employee, product, and sales, and then office. There are total 1 to 6 the tables. And each table has at least one index. But index A, from index A, B, C, D, E, F is an index table based on primary key for direct access. Okay, so salesperson number is a primary key. So using these salesperson number, we create index. For example, A. The second table, customer number is a primary key. And using this customer number, we create index, the customer table. The others are the same. But sometimes application requires a joins. The join is, if you have a lot of join, the performance will be the bad. It's worse, getting worse. But application requires joins of the salesperson, this table, and the customer table. And then salesperson number attributes would be a good choice. Okay, so here, if you combine two tables, this one and this one, but the salesperson number, that one, is frequently used in your statement, the request, the query. In that case, we are able to create another additional index using salesperson number. It's called index G. That means table can have at least one index. Okay, this one. And also, if we frequently need to find salesperson record by salesperson name here, but the users try to find the salesperson number frequently. But in that case, for better performance, can create another index by salesperson name. Okay, so in this case, just add index, this kind of index. We don't change the table itself, just add index. So that means it does not change the logical design. Make sense? Then view is kind of read-only table. So view doesn't store the data itself. If you have table like that, maybe ID name, email, address, and GPA, and so on and so on. Okay. The view means the user's request ID and the email and the GPA. In this case, create read-only window, ID, email, GPA. Just copy the record like this. So that one can be used instead of this. Why? If we wrote this big table into the memory, the performance would be the worst. But this is a small size of table. So it's more lightweight than this one. So, but this is called the view, read-only table, portion of the specific part in a column, okay? So it doesn't change the table itself. So it does not change logical design. Then reorganizing store data. Think about that. This is the hard disk drive. One data, the ID data is stored there. This is ID. And name is stored there. So after searching ID and then try to find the name, what kind of time we need? Searching time. Searching time means in a hard disk drive, there are the cylinder, the platter, and each the platter we have like arm mechanism, right? Right? That means this is the mechanical time. Mechanical time is much slower than electrical time. So to find from ID to the name, maybe we need a millisecond, something like that. This is additional time. So in terms of the performance getting worse. But if we store ID name followed by something like that, we can save this time, right? Just immediately you can find ID and the name and other maybe email and so on and so on. Okay. This is a physical storage. Okay, so cluster the related data on a disk that is reorganizing stored data. It doesn't affect the table itself, logical the database design like this. Salesperson followed by customers. But this is not a table. That is the order the data stored in a physical memory, physical the drive, hard drive. Okay. And horizontal partitioning and vertical partitioning means so horizontal partitioning is rows of the table are divided into groups, and the groups are stored separately. For example, assume that record for sales manager access more frequently than other customer employees. Maybe here, sales manager. So these records are accessed frequently than other records. In that case, split table. One table, sales managers, the others. Okay. If so, most of the requests will use this table. That means we don't have to search unnecessary record. Means can save reduce the searching time. And the vertical partitioning means separate group by the columns like that. Salesperson number, name, year of hire, commission percentage is a one table, but commission percentage is frequently accessed. In that case, the columns are separate. Here, salesperson number, name and hire column, salesperson number, and then commission percentage column. So in this case, this table infrequently accessed, and that one is more the frequently accessed. Okay, means reduce time. Okay, the splitting of large text attribute is similar. If there are the original table, there are column, maybe description table, and there are long strings over there to explain these records. In that case, we split this part, okay, to reduce time, split off large text attributes. So that one is similar, the vertical partitioning. Make sense? Okay. Next one is physical database design affect change the logical design. So you can read the retrieve data of customer, the name of sales responsible. Okay. Name of the sales responsible. Okay. So assume that there's a frequent access to find data about the customers, including name of the salesperson responsible for that customer. So, okay, so in this case, in the original table, maybe here, what is that? Salesperson number, customer number, customer name, salesperson number. Okay, salesperson number can be used as a foreign key, but there are a lot of access using salesperson name. But in that case, substitute salesperson or what number by with salesperson name. This one. In this case, what happened? We have to modify table. So column is changed by salesperson number to salesperson name. That means we have to change the table itself. So this changing attribute changes the logical design. Okay. Then create new primary key. For example, if we have a composite key, combination of 2, 3, or more attributes, but from the performance point of view, if performance is not acceptable, we have to create our new primary key. For example, in this table, without the original table is like that. Then primary key is a composite key, customer number and employee number. But as I mentioned here, the performance is not good. Instead of composite key, we generate new key, customer employee number. So that means new primary key is added into the table, which means logical database design should be modified. Make sense? Okay. And then storing derived data. Think about that. This is an assumption. Some code requires performing calculation on the data and return to calculate the value. But same value have to be calculated over and over many times. So to reduce time, the calculation time, we store that the calculate the value and then add to the table. For example, if we want to calculate total amount to each salesperson, this is a salesperson table, but try to calculate total amount of each salesperson. How? We have to combine customer table and then salesperson. If salesperson has maybe 10 customer, go to the each record and then add the amount of a purchase of each customer and then add 10 records. After that, plus this is the first customer. And then go to the second customer and then add all the amount of purchase. And plus third customer and then add. So the total should be returned to the screen, to the user. But if this kind of request is frequent, every time the request is received, the DBMS doing same operation, that means performance getting worse. So in this case, we add another attribute, total annual customer purchase. And then once the total annual customer purchase is determined, add over there, maybe 1,000. So if a request is received, just search and then return without any calculation to reduce the time. Okay. Okay. Then, absolutely, obviously, if the two tables are combined, we have to redesign our logical database. For example, combination of tables, one-to-one relationship, alternatives for repeating group, denormalization case. Okay. So there are basically, original table, we have two tables here, salesperson and then office. So if you try to find office number of each salesperson, we have to combine this table and then this table. But especially one-to-one binary relationship, we combined. This is a salesperson, this is a office. Okay. For what? Performance. Okay. In this case, we don't need the join operation. You can reduce the time. Repeating groups, just take a look at this one. It's not difficult. Maybe, let me see, time 35. Denormalization. So the physical database design is always a thing, the performance, especially what? Remember? Response time. That is a key metric of the performance. And maybe another one is what? Throughput. Okay. So always this is a performance metric. So when you're performing physical database design, consider performance. It's fast. It's much higher throughput, why not? Okay. So logical database design to remove anomaly and then redundant data. So that's why we split table satisfying normal forms. But physical database design, think of performance, reduced time, return time. Okay. So if unnecessary response time and throughput may mandate eliminating runtime joins. So okay, that is a customer, and this is a salesperson. In the original table, we have, let me delete this card. Salesperson table and customer. We have to join to find the related data of the salesperson and the customer. But sometimes we can sacrifice logical design. How? Bind two tables like this, customer table, salesperson table. But in this case, think about that. One salesperson manages multiple customers. That is one, two, what? Many relationship, binary relationship, right? In this case, we are focused on the many here, and this is one. For example, one salesperson has the multiple customer, so in a table here, this is a customer, and that is a salesperson. So in this combined table, there is a denormalized normalized table. So that one, the salesperson can be redundant, like baker, 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 and the baker. That means baker has 4 customers. Here, this one, and this one, this one, and then this one. Why? We combine the table for performance. Why? If we combine the table, we don't have to do join. Make sense? But in this case, we just maybe less than 10 record. But if you use the database system or other system, we always think the extreme case. If you have like Amazon, maybe 500,000 salesperson, and each salesperson handle maybe 100,000 customers. That means in a salesperson table, the number of record is 500,000. And then customer table, how many? 100,000. So to join to table, how many operations we need? Times 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 5 times 10 to the power 10 operation we need. How long? Maybe hours, maybe day, maybe week. Those kind of the response time, the throughput is now acceptable. So, but if we combine into the one, we don't use join. So just pinpoint the record and then find customer and then salesperson directly. That means reduce time, reduce, improve performance. Sense? Then adding table. So, okay, so to maintain performance, response time throughput, the number of application, and user trying to share the same data is beyond the capacity. So usually, the big tech companies has a lot of the data center, many areas. Like one is, for example, Amazon, maybe Seattle and Georgia, Atlanta, and Chicago, and Dallas, and maybe New York. And then they are synchronized. If there are table, but now always, if the table is updated, they are updated at the same time. That means use the same table, same database. So if not, if we have just one data center, all requests, nationwide requests can be accessed to that data center. But that system cannot accommodate a lot of the requests. So the goal is to reduce. If you are here on the Robbins, we don't have to access the Seattle system. You can access Atlanta system. If you live in maybe Washington, DC, DC users use the table. That means we can distribute requests. Okay. So that means we are able to improve the performance. The throughput will be increased. Okay. So that is cost down. So again, the for physical database design, what is the most important thing? Performance. So to improve the performance, we sometimes may sacrifice the logical database design. Okay, but some of them does not change logical database design, but some of them change logical database design. Okay, so that is the core of the physical database design. Then maybe 15 minutes relax. Like to give one exercise. Okay. So it is related to uh, create the hash, the index table using B plus tree. Do you have the papers? Maybe. Okay. Let me. Do that. So take a look at this question, and then uh, solve the construct of P plus tree, the index table. And this is question number 1. And question number 2 is, so to the this index, when you add 350 to the P plus tree index, what happened? So assume that cylinder 4 is completely full in this case. But if you add 350 to the completely full P plus tree, what happened in our index tree? Okay. Yeah, yours. It's going. Sure. So, B plus tree, so each node can have at up to 4 key and value pair. Okay. That means nodes have 4 elements. Okay. It's up to maximum. This is a key and the value. Key 2, value 2, key 3, value 3, key 4, value 4. So key is what? In this case, locker number. Okay. And then value is what? Cylinder. Maybe kind of cylinder. So try to draw this kind of the P plus 3 index table. Okay. So what are the K1, K2, K3, K4? Then what's a cylinder? Doing good? Yeah, is that this Q1? Yes, you're working on Q2? Okay, okay. But think about that. Each node can have up to 4, but in this case, 1, 2, 3, 4, 5. Can have 5 pairs. So what happened? How's it going? Oh, really? Sorry. Okay, so compare what you have done and mine. So Q1, did you draw like that? What is the 160 and 240, 320, 400? There's a key, key. So which key, which locker number? The maximum locker number should be inserted into the node. Make sense? Minimum, yeah, you can implement using the minimum, but basically, according to my presentation, we use the maximum. Okay, but if you use the minimum, you have to modify uh, the P plus tree itself algorithm to search algorithm. But it makes sense. It's up to you. If you try to implement like that, you can do that. But I try to explain based on my presentation using the maximum value. So in order to find, for example, 230, what happened? Compare 230 in the first key. So 230 is greater than 160 is greater than 230. So go to the next. 240 is the first greater value than 230. So 230 will be located here. But this is a maximum locker number. That means 230 will be stored cylinder, second cylinder there. And then repeat the same process inside the second cylinder. Okay. Erase. And then next one, try to add 350. But assume that cylinder 4 is completely full. There's no empty space to store 350. So what happened? We have to, yes, split. Split means we can use another cylinder. So here, 321, 400. So I evenly separate. How? 321 to 360, 361 to 400. This is for cylinder 4, and this is cylinder 5, new cylinder. Okay. And how many cylinder we use currently? 1, 2, 3, 4, correct. 5. So we have to insert the maximum number 160, 240, 320, 360, 400 like this. Oops, like that. But it doesn't make sense. Why? Each node can have up to 4 key value pair. But how many here? 5. So we have to add one more layer like that. Split these nodes, one part and the other part. So this first part, this one, the second part, and this one. But there's no root. So we have to create a root, the higher layer here. So that is the maximum value, 320, 400. So create another layer and add the maximum. So this is the value indicating this node, and this indicating this node. Make sense? Okay. So previously like that, but after adding 350, the index is 2 layer. Then cylinder, 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 and cylinder, cylinder, like this. Okay. This is a B plus, updated B plus 3 index. Okay, that's all. And then maybe one more, maybe some guy already late. So today is the last day of this semester. Okay, so the very last week, well, we don't have the class. Okay, next week is a Thanksgiving holiday. So no class, but in the from November 29th, December 3rd, we don't have class. So doing final project and the final assignment, the replay assignment. Okay, you don't have to come. maybe the December 2nd, I think. Okay. So that's all about this course. How's it going? Not on me, all of the courses are stressful to you. Okay, so I hope this course is helpful for your the knowledge and then the techniques. Okay, so but that course is just a little bit of the database. Just focus on relation database, but there are a lot of different kinds of database and much more content about that. So based on, if you're interested in, can study more. Okay, so thank you for attending course this semester. Then I hope you guys see you next semester in the different courses. Maybe not. Okay. Any questions? Mhm. Next, computer science 2. Oh, what else? Data structure, database, advanced software engineering, distributed enterprise software design and development. Okay, thank you so far, and then have a great holiday, maybe next week, and then do your assignment and then project, and then one more thing. So I have to grade your work, and I have to report your grade to the MGA. So the MGA has the fixed hard deadline. So no late submission is not allowed. Okay. So I'd like to give extension, but due to the schedule, I can. Okay. Please keep in mind the due date and then submit by the due date. Make sense? Okay. Thank you, guys. So good evening.